Hello. This video is about Lorentz and Poincare group. However, it's divided into three parts. The first part I will talk about a brief introduction of representation theory, and then a brief introduction about Lie groups, and lastly we'll discuss Lorentz and Poincare group. The reason why I would begin with a discussion of representation theory and Lie groups is because these are important topics that are not fully covered in previous videos, and we cannot start our discussion on Lorentz and Poincare group without a basic knowledge of representation theory and the theory of Lie groups. This video is going to be a little bit long because I want to derive everything, and also this is a very important topic and I want to do it justice. So let us begin by defining what is a representation. The representation of a group, which we call G, is defined as a homomorphism which is a surjective, which can be understood as a surjective map from the group G to general linear group of dimension V. GLV stands for general linear group of degree or dimension n. Actually, here we use dimension V. In other words, it's a group of all the V times V invertible matrices. So each under this representation or this mapping, each group element G goes into a matrix, DG. We use the letter D normally to denote representation, which is an element of GLV. The properties of a representation of a group is the same as the property of the group itself. First of all, we have this multiplication rule. For representations, they're matrices, so naturally they will just follow the multiplication of the matrix. And then there's this identity. For a matrix, the identity is, of course, the identity matrix, and we normally map the identity of the group to the identity matrix. Another important property, the inverse. The inverse is simply the representation of the original group element inverse, because remember, GLV is the set or the group of invertible matrices, so we're allowed to invert this representation DG. Lastly, the associativity. This follows trivially from the fact that group multiplication in our representation simply becomes the multiplication of two matrices. Now that we've seen what is the representation, we define a very important class of representation. They're called reducible representations. A representation D is reducible if there exists a non-trivial invariant subspace U. By non-trivial, I mean this subspace is not zero. And also it's a subspace, so it cannot be the original space itself. In terms of, in the language of matrices, this can be simply put as if the representation is reducible, it means that the matrices of this GLV is reducible. So those matrices can be reduced into this block diagonal form. This D1, D2 are blocks. They're matrices. They're not just an one by one element. And the off-diagonal elements are zero. If we are not able to reduce this representation into the block diagonal forms, then the representation is said to be irreducible. So otherwise, if we cannot reduce it, D is irreducible. And for short, we call this irreducible representation irrep. This is just a shorthand of irreducible representation. And as we can see, reducible representations can be constructed as a direct product of irreducible representation. For example, in this case, this is simply a direct product of D1 plus D2 and plus everything that is in these dot, dot, dot. So it is irreducible representations. It is the irreps that are more fundamental, and hence they are of the most interest to us. So that is our very brief discussion of the representation theory. Now let's jump to the second point on our agenda, introduction of Lie groups. The formal definition of Lie groups involves the introduction of many mathematical concepts such as manifold, compactness, connectivity. So I'm going to introduce it in an easier way. So first of all, it's important to know that Lie groups are typically infinite groups, which means it has an infinite amount of elements, and it's normally called a continuous group. Ooh. So instead of giving a formal mathematical definition, I'm just going to show how do we construct a Lie group, or in other words, what is the structure of a Lie group. To construct a Lie group, we first need building blocks. And these building blocks are called generators. They can generate all of the group elements of a Lie group. And we call these generators xi. So we have many generators, and they're indexed by this index I. And the important note here is that the choice of generators is not unique. So the generators, I'm going to write this again, is not unique. Generators actually forms a space of itself. So, for example, if we choose these xi's, they sort of form the basis in this space. And then you can do a basis transformation to give you your preferred set of generators. And this property is going to be very useful when we talk about the representation of Poincare group. Now that we have generators, For each generator, we need to give it a parameter. Let's just call them alpha. And these parameters are numbers, and they're continuous. And that is why a Lie group is normally called a continuous group. So now that we have generators and we have different parameters, we need to construct each element of the group. And this is typically done by what is called an exponential map. This tells us that each of our group elements, in this case, we jump right into the representation. The representation of each group element can be expressed as a function of these parameters. And it is equal to the exponential of I times these parameters times the generator. So here I used the Einstein notation, so the summation over I is assumed. There's a theorem that says if the group G is a compact and connected Lie group, then the exponential map covers the entire group. This gives us a justification of why we use this exponential map to express the representation of all of the group elements in our Lie group. However, it is very unfortunate that the requirement of compactness and connectivity is not exactly met by the Lorentz group, which we'll see very soon. But we can reduce our Lorentz group into a subgroup that is called the Poincare group that satisfies these properties. So, and we will mostly analyze the Poincare group. So this approach will be used in this video. And now that we defined, at least we've shown the structure of a Lie group, we introduce, I would argue, the most important idea about Lie group is the Lie algebra. The generators of a Lie group, they follow Lie algebra. So Lie algebra is an algebra for the generators, and Lie algebra is a characteristic idea of the group. So it's independent. Lie algebra is independent of the representation. Lie algebra is the fundamental characteristic of our Lie group. So what is it? This is xi, xj is equal to I times f I jk xk. So these I and j, xi, xj, and xk are different generators, and this bracket means commutation. And this f is the structure constant. The structure constant. And all of these structure constants, they basically program your Lie group. So another way to put it is that they would completely define the Lie algebra. The properties of our Lie algebra. The first is antisymmetry, which means that if I swap these two generators, I'll get a minus sign. Second, and actually the most important or the most fascinating is the Jacobi identities. And this identity is widely used when you study quantum field theory. It says xi, xj, xk plus xj, xk, xi, running out of space, plus xk, xi, xj is 0. This is a famous Jacobi identity. And the last one is linearity, which is kind of trivial actually. It simply means that you can add them linearly. All right, so that concludes our very brief introduction of Lie algebra and of Lie group. So now it's time for us to dive into the Lorentz group, which is the main topic of this video. So as we've seen before, Lorentz transformation looks like this, and this is our Lorentz transformation. And all the Lorentz transformations form a group, and it's called the Lorentz group. As we've seen before, these Lorentz transformations satisfy two properties. The first of which is that the determinant of this Lorentz transformation is 1, and then we also have this identity. These eta are our Minkowski matrix. Well, actually, I made a mistake here. The determinant is plus or minus 1. These two are the properties that we know from our discussion of Lorentz transformation. So now from property 1, we can see that there are elements with determinant 1 and elements with determinant minus 1. And the elements with determinant equal to 1 forms a group, which of course is a subgroup of the full Lorentz group, and is called SO13. And the English name is proper Lorentz group. And the elements with a determinant equal to minus 1 forms the improper Lorentz group, which, mind you, is not a group, right? We call this improper Lorentz group, but it is not a group because it's not closed. If you have two transformations with determinant minus 1, and then you combine them, it gives you a determinant of 1. So this improper group is not a group. But the proper group is. So this is so this is what the first identity tells us. The second identity, if we examine the 0, 0 component, which is the time component, 0 means the time component, we find that the left-hand side gives us 0, 0 squared minus I zeros, so the i's are summed, which the right-hand side gives us 1, where the I is the spatial coordinate, so it runs from 1 to 3. This means that the zeros component is 1 plus 1 plus this, which is greater than 1 because this is a square. It's greater than 0. It's greater than or equal to 0. So this the 0, 0th component of Lorentz transformation squared is greater or equal to 0, and that gives us two options. Either is greater or equal to 0, or it's smaller or equal to minus 1. So, and we give them names, transformations with 0, 0's component greater or equal to 1 are called orthochronos, and normally we use an upper arrow for them, and those with the 0, 0 component smaller than minus 1 are called non-orthochronos, and then and we give them a down arrow. So now we've seen the structure of our Lorentz group, which is divided into 4 parts. Lorentz group with plus determinant and orthochronos Lorentz transformations. Lorentz group with minus determinant and orthochronos transformations, plus determinant non-orthochronos, plus determinant and minus determinant and non-orthochronos. So we can make a table. This is greater or equal to 1 because it's orthochronos. These are smaller or equal to minus 1. And the determinant. And also we can ask whether or not it's a group. This guy is a group, and none of these are groups. They're just parts of our full Lorentz group. So this guy is the most interesting one. The proper orthochronos subgroup of the full Lorentz group, we give it a name SO13, is the proper. Remember, proper means determinant is positive, or determinant is 1. Yeah. Orthochronos, which means that the 0, 0's component is greater or equal to 1. It's a proper orthochronos subgroup of the full Lorentz group. It also has a name because it's very important. It's called the Poincare group. And now, because it's extremely important, and most of the interesting physics happens in this group, it is often referred as Lorentz group. So this Poincare group is often referred by professional physicists as Lorentz group. But in this video, to avoid confusion, I will try my best to call it Poincare group from now on. But normally when one talk to people, is generally just referred to as Lorentz group. So now let's see. We divided the Lorentz group, the full Lorentz group, into 4 parts: the Poincare group, and the other 3 parts that by itself are not groups. So now let's see how they're related to each other. For example, the transformations that we did not include in this Poincare group, the interesting ones, are parity, which is this, time reversal, and PT, which is parity times time reversal. The parity, apparently if you act the parity, the determinant of parity is -1. So if you act parity if you combine parity with another Lorentz transformation, you get the determinant, the determinant of the product will be -1. So it sends the proper orthochronous subgroup to the improper, but still orthochronous subgroup, because the 0,0's component is not changed. As for time reversal, the 0,0's component is changed. It's timed by a minus sign, so it becomes non-orthochronous. The determinant of this time reversal is also -1, so it also becomes improper. PT, by a similar argument, changes the sign of the time, the 0,0's component, but it retains the sign of the determinant, because we have 4 -1s. The determinant is 1. So the full Lorentz group is a product. The full Lorentz group is normally called O13. Is a product of our Poincare group as O13, and also the upper arrow for orthochronous, times this other group, which has 4 elements: the identity, parity, time reversal, and PT. This is a full structure of of the full Lorentz group. But the interesting bit is here, is the SO13 orthochronous, which is a Poincare group. So now let's focus on this interesting bit, and first look at the Lie algebra of our Poincare group. To derive the Lie algebra, I'm going to introduce you a method that is very useful in these kind of calculations, and also can be applied elsewhere when you're dealing with other Lie groups. So first, let's consider an infinitesimal transformation apologies, around the origin, which is the identity. Our Lorentz transformation becomes identity, which is expressed as a delta, plus this infinitesimal transformation. This is infinitesimal, which means that this omega is very small, and plus a term that is of order of omega squared. It's small, so omega squared is even smaller. We can use this identity that we discussed before. Actually, I don't want this to be a mu. That to be a nu is alpha beta. We can plug this in with some algebra. We can show that this is true. This is just some TD's algebra, so I'll skip it and only show the result. Now we can cancel out these two terms. And to the first order of omega, sorry, we get omega mu nu plus omega nu mu is 0. In other words, omega is anti-symmetric. So now let's rewrite omega in this form because it's anti-symmetric. We can introduce a bunch of deltas. Now, let's look at this. We identify this as our generator. We'll give it a name called J. And we copy it down. And you notice that I added an additional factor of I in front of it. This is because we want to make the generator J ij Hermitian. These J's are generators. Right here, we identify them as generators, and we add this I to make J ij Hermitian, whereas before I and J are the this is not very good mathematical grammar. I and J runs from 1 to 3. They're the spatial coordinates. So this gives us, if we plug back in to our original infinitesimal transformation, this gives us the identity is still the identity, and we have this omega here, and our generator d mu nu. Right. So then we notice that this is really the generator, and of course we have a omega squared term, and these omegas are our parameters of the Lie group. So in general, this equation is just for one generators. In general, if we have many generators, and for the full group, we can use the exponential map. To construct the full group with all the generators and the corresponding parameters, omega, and these alpha and betas are summed over. Now, we classify our generators into two categories. We identify Gij as rotation generators. I apologize for this. As rotation generators, where of course I and J are our spatial coordinates. There are a total of 3 rotational generators. This is because if they're the same, it becomes 0 because If you look at the definition, these two terms are literally the same. And then this generator is anti-symmetric. So we're only really left with three of them, which is J12, J13, and J23. So there's a total of three rotational generators. We also identify Ji0 as boosts or boost generators. Again, this I goes from 1 to 2 to 3, and J0I is just minus Ji0. So there's a total of three boost generators, and J00, of course, is just 0, so we don't need to consider them. So this is how the generators are classified. Now let's go to the Lie algebra. The proof or the derivation of this Lie algebra is a lot of tedious calculation, which I will just skip for now and provide the result. Minus, let's see, mu and rho, mu sigma minus mu sigma j mu and rho. Right. So this is a Lie algebra of Poincare. This looks very complicated and difficult to deal with. But they're good news. We can simplify them. And that brings us to the topic of representations of the Poincare group. Let us now redefine our generators by timing our rotational generators by timing our rotational generators with this epsilon, and leaving our boosts unchanged. So these are the rotations. And we can see that these matrices are Hermitian. You can prove it almost trivially. And the boost generators are anti-Hermitian. And if we plug these two expressions into our full, complicated, long equation of the Lie algebra of Poincare group, it simplifies into three equations. I apologize for this. It simplifies into the J's follow this Lie algebra. The J's and K's follows this, and the K's has a minus. Let me just write in a prettier way. The K's has a minus, so the algebra reduces to this. The interesting feature is that for the J's, we obtain the Lie algebra of a SU2 group, which we're familiar with from when we're learning about spin in quantum mechanics. But the J's and K's are still mixed with each other, and it's rather difficult for us to deal with this. So let's redefine them. We redefine our generators into J plus or J minus, defined as Ji plus or minus I Ki. The factor of I is because, remember, these boosts are anti-Hermitian. So we want to have this extra factor of I so that our J plus minus are Hermitian. Hermitian. And if we do this, we can further simplify our Lie algebra. Into this. Jk plus or minus Jj minus plus is 0. Now this looks very interesting. So the first equation is the Lie algebra of SU2. This is equivalent to the integer or half-integer spin in fundamental quantum mechanics. And both J plus and J minus follows this Lie algebra. And the second equation tells us that these two sets of Lie algebras, the J plus and J minus, are independent of each other, which means that they commute with each other. They're not talking to each other. They're commute. They're independent, which is great. It means that we can actually decompose our Poincare algebra into two independent SU2 algebra, which in this case we call it sub-algebra. Yeah, so it means that SO13 can be decomposed as two SU2s. However, we need to be very, very careful about this statement. This decomposition holds at the Lie algebra level. So right, we can decompose the Lie algebra into two SU2, and they're independent. They don't talk to each other. But this doesn't mean that the group, so the group itself, the Poincare group itself cannot be expressed, say, as a direct product of two SU2s. Right? It means that if we say that this is equal to the direct product of SU2, it's wrong. This is not equal to. So this decomposition only holds at algebra level. Nevertheless, it's a good thing because we can now construct all the representations of our Poincare group from the representations of SU2, which we're familiar with from our study of spin quantum numbers. So this allows us to construct all representations of our Poincare from SU, suspicious looks like a O, SU2 representations. What does it mean? It means that we can label our representation of the Poincare of our SO13 by two numbers which correspond to the representation of SU2. So we can label them by J minus and J plus, which are half integers or integers, pretty much like we do for spin quantum mechanics. And this gives us very interesting and profound consequences. And now I'm going to show you an example. The example is that it actually can label particles, and those particles and the numbers, the J plus and J minus, are related to the dimensions of the particle, and is intimately related to how we treat them. For example, in quantum field theory. So we can make a table, J minus J plus, starting from the easiest one, we have 0, 0, which correspond to the spin zero case of fundamental quantum mechanics. And then we can have 1/2 0, 0 1/2, and we can have a combination of 1/2 0 with 0 1/2. We can have 1 1 and so on and so forth. Let's look at the dimension of these representations. 0 0 of course is one dimension. The type is a scalar. One dimension, it's a scalar. For 1/2 0, it becomes two dimensions. Similar for 0 1/2. So these are called left-handed spinners or right-handed spinners. And the fourth one, 1/2 0, direct sum with 0 1/2 has a dimension of 4. And they are called the direct spinners. 1 1 has a dimension of 9, and they're represented by tensors. So that's very abstract. Give an example. The example for a scalar, in particle physics, we have pi's. And the most famous example is the Higgs bosons. The left-handed spinners, the most famous example are neutrinos, and their antiparticle are right-handed spinners. The direct spinner is the most common. We deal with them every day: electrons, positrons, protons, and neutrons, and they're all direct spinners, and they're expressed by a four-dimensional vector. And that is why when you study relativistic quantum mechanics, your Dirac equation is a 4x4 linear operator, your Dirac Hamiltonian. And for the tensors, one example is graviton. So this shows that our decomposition of the representation of the Poincare group can lead to very interesting physics. It helps us classify particles and all that. And this conversation, this discussion can keep going, and it will eventually lead up to a beautiful theorem by a brilliant female physicist, Emmy Noether. It's called the Noether theorem. It says the symmetry, which is represented by the group by our groups. Symmetry means that if something is conserved, if something is invariant under a group transformation, then we call this a symmetry, and Noether's theorem says it represents the conservation of a physical quantity. It's a very beautiful theorem, and this is where this discussion should lead up to. However, we don't. That will be a very long discussion, and I'm not going to dive into it right now. So for today, this is all. Thank you very much for your time.